Okay, so continuing from the previous lecture, we're going to find the in order to add, subtract, in particular to divide complex numbers, we need to know the concept of complex conjugate. Now, z is the complex number a plus bi, a units on the real axis, plus b units on the imaginary axis. Its complex conjugate is defined as a minus bi. That means a units on the real axis and minus bi units on the imaginary axis. Their product, what is their product? It's a plus bi times a minus bi. That's the same as a squared. If you notice, this is the difference of two squares. Complex numbers, when it comes to arithmetic with complex numbers, they obey all the same rules that real numbers do. So in particular, difference of two squares becomes the difference of two squares, a plus bi times a minus bi is the same as a squared minus bi in parentheses squared. So it's a squared minus parentheses bi in parentheses squared. Notice, what is this? This is b squared. So we're actually subtracting b squared times I squared. I squared is negative 1. B squared is, I squared is negative 1. Negative 1 times negative 1 is a plus, so it's a squared plus b squared. Which is the same as the absolute value or the magnitude of the complex number squared. So this is a real number. So with this in mind, we're going to find how, we'll first define how to multiply complex numbers, then using the complex conjugate we can define how to divide two complex numbers, and then addition and subtraction will just be pretty much a pretty straightforward continuation that's just done component-wise. So let's start with the less straightforward task of multiplication. A plus bi times c plus di, so this is, say, z1, this is z2. What is their product? Well, you can follow this out. A times c plus bi times di plus what? Plus bi times c plus a times di. If you notice, it doesn't matter which order we multiply these things in. So we can switch the order. This becomes b times d times I squared. AC plus BD times I squared plus AD plus CB times I. So that's the same as AC minus BD AC minus BD plus parentheses AD plus CB times I. This is a real number. This is a real number. So notice when we multiply these two complex numbers, what do we get? We get a complex number. AC minus BD, this is a real number. AD plus CB, this is also. So this is their product. Now we can use the complex conjugate to define complex division of complex numbers. So again, z1 is a plus bi, z2 is c plus di, z1 over z2, that's the same as z1 over z2. We can multiply numerator and denominator by the same thing, let's say by z2 bar. Notice magnitude is always a positive number. In particular, it's a real number. So this is the same as z1 times z2 bar all over the magnitude of z2 squared. We know how to multiply from two complex numbers. This is just the product of two complex numbers. So it ends up being a plus bi times c minus di all over c squared plus d squared. Okay, and then you can just multiply this out by foiling. I'll let you do that for on your own for an exercise. But as you see, we already foiled these two out. It's pretty much the same thing, just now instead of multiplying bi times positive di, you multiply bi times minus di. Okay, so that's division. This is how division is defined. Okay, so if we FOIL this, what we end up with, it's very similar, it just becomes AC. Instead of minus BD, it's plus BD. And it is, this becomes BC minus AD times I all over C squared plus D squared. So we divide by, this is the same as saying, okay, this real number divided by C squared plus D squared, plus this real number divided by C squared plus D squared. So let's summarize what we got, what we found out. AC minus BD plus I times AD plus BC, or AD plus BC times I. That's how we multiply. How do we divide? How do you divide two complex numbers? Well, so again, I think what's important, you do this on a sort of case-by-case basis. Memorizing this formula can be kind of tedious and annoying. If you're welcome to if you want, but it might be easier just to memorize multiplication FOIL. For division, multiply numerator and denominator by the conjugate of the denominator. But I'll leave those up there as addition and subtraction. This is actually a lot quicker. You can just add them component-wise. A plus B plus C plus DI. And then subtraction. So these are all the formulas for multiplication, division, addition, and subtraction. This is just component-wise. You add, say, a plus bi plus c plus di. It's the same as adding a plus b, two real numbers, and then adding the two coefficients of imaginary numbers, and multiplying by I. Same thing with subtraction. So subtract the two real numbers, subtract the two real numbers that are coefficients of i's. Voila, there's your answer. Multiplication and division, formulas involve one more. Now there's really just one more formula that's really, the book goes over a few formulas. There's really one formula that's really important for higher order ODE, and we'll go over it. We'll go over it now. That's the following. E to the I times z is equal to cosine z plus I times sine z. So it's actually possible to find cosine sine e to a complex number by series. E to the z is defined as 1 plus c over 1 factorial plus c squared over 2 factorial, etc. Cosine z is defined by So, provided these series converge, you can define cosine and sine. What's really important here is this formula. This is called Euler's formula. Cosine theta plus I sine theta. So this actually means e to the I theta lives on the unit circle. And you can define, here's how you define e to the z. It's actually defined as e to the a plus bi. So it's defined as e to the a times cosine a plus I times cosine b plus I times sine. This is actually the most important, because this is what we're going to see. This will come up when we get to solutions of higher order of these.